Greetings, this is Matt Roscoe from the University of Montana with a lecture in our calculus course on the trigonometric function, section 3.5. So let's dive right in. So today what I'd like to talk to you a little bit about is an informal derivative of the sine function. And then once we have the derivative of the sine function, we'll use it to find a derivative of the cosine and derivative of the tangent. We'll do a few examples. But of course, since all of this will rest on an informal derivative of the sine, something we're kind of guessing at or looking, I guess, accepting without a lot of proof, at the very end, what I want to do is give you the formal justification for the derivative of the sine. So something like number 5, you probably never included in a test setting, but, we just don't want to build our mathematical future on a rocky foundation. So it'd be nice to make sure that we know for certain that the derivative of the sine is what we think it is when we informally derive it here in a second. All right, so that's a brief overview of where we're heading. Let's dive right in. All right, so let's use this Desmos link to make a conjecture about the derivative of the sine by inspecting the graph of the sine function. So we'll go ahead and go to the link here and pull it down. This is where the link gets you to, and I guess you can see I have some sort of a point that I'm gonna drag along the function, or since we're only going from roughly positive pi to negative pi, I think I'll adjust this to be 2 pi, negative 2 pi to positive 2 pi. And we could probably do the same for adjusting, these x-axes. Let's let the step be in terms of pi. So that might help us sort of see what's going on. Okay, there it is. There's the sine curve that we all know and love. Period is 2 pi, amplitude is 1. If I play the player now, we'll have this point that sort of gets played along here. I'll adjust the speed down a little bit so we can kind of watch it more slowly change. And now the idea would be, okay, what happens if I add a tangent line to the graph and think about its slope as the derivative? So maybe the place to start would be to come back here at 0 and think, okay, so right away we can see that whatever the sine's derivative is, its slope at 0 is not going to be 0 like the sine function's value. The slope of the derivative of the sine function is going to be positive, so it'll be somewhere up in here, and it will actually be positive and then decrease to 0 right in here. So at pi over 2 we'd see it sort of come down and decrease to 0, and then it would become negative as I proceed from there to pi, and negative and sort of maximizing until maximum negative right there at pi. So and then it'll increase concave up and back to 0 at 3 pi over 2, so the point 3 pi over 2 will be on the graph, and then increase again to some sort of maximal value right there at 2 pi. So again, just to sort of sketch it out, positive, decreasing to 0, negative, decreasing to a negative value, maximal negative value, and then increasing back to 0 here, and then increasing back to its positive maximal value there. So I don't know if you can picture that in your head, but let's go ahead and put the point in that is the actual slope value of this black line. Maybe we should make the black line orange too, so that we have a sense of what's what here. Actually, I don't like orange. I'm going to do blue for both of them. Just can't see the orange versus the red very well. And we'll do this point as blue as well, so that we have everything. So the value of the blue line slope is shown here in this point. So the slope is coming down to 0 right there, decreasing down to a maximal value here, then increasing back up to 0 here, and then increasing to a maximal value there. So we get something that looks like that. If we go ahead and plot it, this is what it looks like plotted. I'll make it blue. So again, here's what we're thinking. Let's go ahead and let it run its. So again, steep negative slope there, adjusting back to 0 here, and then positively valued slope, but decreasing as x increases to 0. Now a negatively valued slope increasing to a maximal value there. And now a negative value slope 0 back to positively valued slope maximal, decreasing back down to 0 right there, decreasing back down to a maximal negative slope right there, increasing now back to 0 right there, and increasing up to a maximal value right there. So there it is. That's a graph of the derivative of the sine function. And we definitely have something that looks cyclic as well. I mean, it makes sense that, since the sine slope is cyclically changing, that its derivative would be cyclically changing. And hopefully at this point it's just screaming out to you what the derivative of the sine is. And I'll let you fill in the blank there. But the derivative of the sine turns out to be the cosine. So based on our investigation, there's really strong evidence that the derivative of the sine is the cosine. I mean, just to drive the point home here, over the top of the derivative function, we could plot, I guess we've got hg, I don't know, r of x maybe, oops, equal to the cosine of x. And you can see that over the top of that, let's make it green, over the top of our derivative function, cosine seems to fit just perfectly. So there's pretty strong evidence based on this technological investigation that the derivative of the sine is indeed the cosine. Okay, so let's try to use that relationship, the derivative of the sine equals cosine, to show that it turns out, to show or prove that the derivative of the cosine is negative the sine. Turns out the derivative of the cosine doesn't get you right back to sine, it gets you to the opposite value of the sine, negative sine of x. So let's do that first, make that little proof, that little argument. So we have something new there. So let's just think about it a little bit. So this is section 3-5, page 1. What we want to show is d by dx of the sine, the cosine, is equal to negative sine of x. Here's our proof. Well, let's just think about this a little bit. All we really know is that the sine, and all we know, at least in terms of this family, or getting close here, is that the derivative of the sine is the cosine. So maybe the right idea would be to rewrite the cosine of x in terms of the sine of x, right? And we know that the cosine and the sine are exactly the same graph, but one is just out of phase with the other. And it turns out that the cosine is equal to the sine of x plus pi over 2. In other words, all we're going to do is shift the sine graph pi over 2 units to the left, and we actually get the cosine graph. So if we use this fact, so I'll say notice that this is true, right? So what can we say? We can say that the derivative with respect to x of the cosine of x is equal to the derivative with respect to x of the sine of the argument x plus pi over 2, adjusting for the phase shift. And now if we can find the derivative of this guy, we're in good shape. And notice that we have a function that we could get its derivative by the chain rule. So if I take the derivative of the sine, and then chain out the derivative of the argument inside the sine, I can think of this like an f of g of x, right? So I'll just sort of write up above here f of g of x. So what do? We take the derivative of the outside function. Derivative of the sine is going to be the cosine, leaving the inside function as untouched. And then we take the derivative of the inside function. And when I take the derivative of x plus pi over 2, well, the derivative of x is 1. The derivative of pi over 2 is 0, so we get just 1 plus 0, which means that the derivative of the cosine is actually the cosine of x plus pi over 2. And if you think about it, when you shift the cosine pi over 2, what you end up getting is then the negative of sine of x. So in other words, what that does is just shift the cosine graph pi over 2 units to the left, and you end up with a sine graph that's been reflected across the x-axis. So that is the idea, and we've proven the statement. So what do we know so far? Well, we think that 1 d by dx of sine of x is equal to cosine of x, and number 2, d by dx of the cosine of x is equal to negative of sine of x. So we've got 2 of the trigonometric functions, and probably we go after the next one, right? I'll just run back to my slides. We're going to use these 2 relations to find an expression for the derivative of the tangent next. So let's do that. Oops. Let's see what I wanted with this. I guess I could make this bigger too. All right, that's page 2 here. So we want to, what is the derivative with respect to x of tangent of x? Well, again, notice that we can write the tangent of x as the sine of x over the cosine of x. You know that from pre-calculus, that tangent is just the ratio of the sine to the cosine. So we can take advantage of that fact. So if we want to find the derivative with respect to x of the tangent of x, then what we're going to do is take the derivative with respect to x of the sine of x over the cosine of x. And what we notice is that we've got a quotient here, right? So all we need to do, and we know the derivatives of both of these functions, so we should have no problem. So we're going to apply the quotient rule here. It's bottom times the derivative of the top, so cosine of x times d by dx of sine of x, minus the top times the derivative of the bottom, so it'll be sine of x times d by dx of the cosine of x, and that whole thing over the bottom squared. So we get something like this. Okay, so let's go ahead and see if we can shake it out. On top we'll get cosine of x. The derivative of the sine is the negative, or sorry, is the cosine. So that times cosine of x. Here we get minus sine. And we take that times the derivative of sine of x. We take that times the derivative with respect to x of the cosine, and that's negative sine of x. And I can see the negative and negative combine to make a positive in the next step. That's all over the cosine of x quantity squared. So what do we get? We get cosine squared of x plus sine squared of x all over the cosine of x quantity squared. We notice that this thing from our trigonometric identity is just what we call the Pythagorean identity. You know, the right triangle that makes up a piece, a location on the unit circle guarantees us if sine is the y component and cosine is the x component, then what we have is a little right triangle there with a hypotenuse of 1. So sine squared plus cosine squared is always 1. So what we end up getting for our answer is 1 over the cosine squared of x. And that's our derivative for the tangent. Let's see. So indeed the tangent is 1 over the cosine squared of x. And we've got all three trigonometric functions now, so I guess all that's left is to do a little bit of example work. Let's do this first one, the derivative of 2 sine 3x. Maybe before we hop into it, let's go and check it out on Desmos. I don't know. I'll just 2 sine 3x. Let's see, so I'll put 2 times the sine of 3x in here. And what do I notice about the derivative? Wow, it's pretty hard to see right now, but it appears like the derivative is cyclic too, but it has a much higher amplitude. So maybe what I'll do is I'll change our viewing rectangle a little bit. So it looks like we could go from negative, I guess, pi to pi. That might be a little bit nicer, and negative 7 to 7 here. Something like this. So you can see that the original function, which is in red, which has amplitude 2, I want to make sure I have the right problem. 2 sine 3x, yep. So 2 sine 3x is amplitude 2. And it appears that we get another function out that appears to have amplitude 6. And let's see, its period is the same, right? So the period would be the same as the period of 2 sine 3x. I think the 3x, what that does is adjusts our period by a factor of 3, right? So instead of a period of 2 pi, we get a period of 2 pi over 3. And sure enough, there you go, 2 pi over 3 seems to be the period it takes on the original function to come back to where we started. It's also the period in the derivative, which should sort of make sense, right? Because the slopes are changing periodically, as well as the value of the function. So let's see if we can go after this analytically, and we'll come back to add its derivative here once we think we know what it is. Okay, so let's go ahead and switch back over to image made here, maximize, and get after it. All right, so our first example here is to find the derivative of 2 sine 3x. So f of x is equal to 2 sine of 3x. What is f prime of x? Well, that's going to be d by dx of the quantity 2 sine of 3x. I notice right away that I've got a constant which can come out of the argument, so it'll be 2 times the differential derivative with respect to x of sine of 3x. And now I kind of recognize this as a function inside of a function, right? So this is, I guess this is f, then we could call this g of h of x, right? And so for our derivative, what we're going to have is 2 times g prime of h of x. So the derivative of sine, leaving the 3 of x alone. Well, the derivative of sine is the cosine, so we'd have cosine of 3x. So that's the g prime of h of x times the derivative of the inside function. So the derivative of the inside function is just 3, and that's our h prime of x, right? So this idea right here is the chain rule at play. And now it's just clean up the function a little bit. We've got a 2 and a 3 that together make a 6, so it would be 6 times the cosine of 3x would be the derivative according to the chain rule and what we know about the derivative of the sine, and I guess derivative of constant or of a linear function like 3x. Let's see if it fits our function. So the idea would be to come down here and to write our function in as 6 times the cosine of 3x. If I hit this guy, it should then magically overlay, and indeed it does. So it seems like we must have the correct derivative if indeed that function overlays the shape of the graph made by the slopes of the function, the red function. Okay, well that looks great. Let's go back and try another one here. Let's see. Guess I'm right here. Let's try something a little bit more fancy. Let's see. The example here is the g of x equal to the square root of a periodic function. So that'll be interesting to see what happens. The square root of 1 minus cosine x. All right, I got it written down. I can switch over to take a look at it on our function mapper. Square root sqrt of 1 minus cosine of x. Okay, so that's what it looks like. Seems like this guy's period is a little bit longer. Looks like the red function, its period is 2 pi. So let's go ahead and take a look. And it looks like amplitude is no more than 2. I guess so. For the x-axis, I'm going to go to negative 2 pi to pi. To 2 pi. And then for the y-axis, I'm going to get between what, negative 2 and 2 it looks like. There we go. So this is pretty interesting because we end up with a function that has a sharp corner at a point here. So if we kind of think about what's going on here, I guess the cosine is a cyclic function that varies between negative 1 and 1. So we're taking the square root of 1 minus something that ranges from negative 1 to 1. And so it looks like as it comes down here, we're growing to 1, and then yeah, I guess that ends up as 0, so the square root of 0 is just 0. So we have this sharp function. So I guess what we're seeing is that if we think of sort of what's going on here, we come down, we're negatively valued, and then right away we pop to positively valued at that sharp cusp. So that's interesting. That means that our derivative should not be defined at multiples of, I guess, 2 pi, right? Because this happens every 2 pi. That's interesting. Even though the function is defined at 0, it has a sharp cusp at 0. So this is an example of a continuous function that's not differentiable at multiples of 2 pi. All right, well, we're after the blue dotted line. Let's see if we can get it analytically and then come back to check it. So here it is. Here's our function. Let's see if we can put our heads together to figure out what g prime of x is going to be. I mean, probably the first thing you want to do is think about this as a power rule rather than as a square root. It's the same thing as 1 minus cosine of x raised to the power of 1/2, right? And then what I notice is that this thing, again, is like a chain rule sort of situation. We have something in the form of f of, well, I'm not going to use g because I got a g right there. And we've used h and g up here. I don't know, so what, m of n of x. All right, so we're going to have to use the chain rule if we want to go ahead and take this derivative. It says take the derivative of the outside function, which would be 1/2, leaving the inside function alone, 1 minus cosine of x raised to the negative 1/2. Okay, so there's our m, I guess if I had to sort of think about this, this is m prime of n of x. And then I would multiply that by the derivative of the inside function, and the derivative of 1 minus cosine x would be, well, the derivative of 1 is 0, and then we have a minus inside, and then we take the derivative of the cosine, which is negative the sine of x. And this piece we can kind of think of as n prime of x. And so what am I doing here? That I'm just doing the chain rule, right? Taking the derivative of the outside function times the derivative of the inside function. Now I just need to clean things up. Well, let's see. So it looks like I have a positive sine x on top, and on bottom I have 2 times the square root of this argument, 1 minus the cosine of x. A few things sort of pop out to me when I think about this. I can see that anytime this argument is valued at 0, we're going to have something divided by 0, which will be undefined. And of course, the cosine is valued at 0, at 0, and let's see, yeah, the cosine is valued. Oh, sorry, this is only going to be valued at 0 when the 1 minus the cosine is valued at 0, and that's when the cosine is valued at 1. When the cosine is valued at 1, of course, is, well, so when is 1 minus cosine of x equal to 0? That's when cos of x is equal to 1. And if we kind of think about how the cosine looks, right, we have this sort of this picture, right, and this is 2 pi, right, and this is 0. So the cosine's valued at 1 at 0, 2 pi, and every multiple of 2 pi. So that seems to match a little bit the picture we saw in our graph where the derivative was undefined at multiples of 2 pi. So it seems like we're at least on the right track in terms of thinking about, let's see if we've got the right, actually the right function. So it'll be sine x on top, divided by the square root, well, wait a minute, 2 times the square root, 2 times the sqrt of 1 minus cos of x, and drum roll please, boom, we got it. So sure enough, that function, which we could have probably never guessed at just looking at this, right? Much harder function to sort of wrap our hands around, does pop out if we use the correct derivative procedures. All right, so I feel pretty good about that. That looks good. Looks like we must have done the right thing there. Let's go ahead and go back and look at one more example problem. How about the tangent of e to the x? So let me write this thing down first. So if I call it h of x equals the tangent of e to the x. So let's see. Let's see if we can get a sense of what it looks like first. The tangent of e raised to the x. We get this crazy function. So yeah, this is absolutely crazy function here. But what you can kind of think of, I can kind of see this thing right here as a tangent function. Tangent functions have these, I guess, asymptotic behavior. It kind of looks like a cubic function, but it gets repeated, and there are these asymptotes because, of course, the tangent isn't a continuous function. But what you can kind of think about what's going on here is that the tangent is being fed the output of the exponential function, which is blowing up. So what it's doing is really compressing the period of the tangent, and it kind of infinitely compresses it very quickly. So we get this really, I guess, dense function off here to the right. But maybe a better way to think of this is just to see the first few of these. So let's just do this from, I don't know, the x-axis from negative pi over 2 to positive pi over 2. And then let's let the y-axis, though, be quite large so we can see, I don't know, negative 10 to 10. Is that going to be enough? I can't tell. Not really. Let's do a little bit more. How about negative 50 to 50? See what we get there. Okay, so now we have something. So if I move this point along the graph, I can see that the slope of the function is going to infinity right there, and then there's a point of I guess discontinuity in the graph, and we jump back down here and we start at a very high positive number and flatten out really quick until we're to pi over 3, and then start growing again. So it looks like we get something like this, and yeah, so there it is, a picture of a function and its derivative in the dotted blue lines here. Maybe I should make this one just a little bit, I don't know, I was thinking I should make this one distinguishable. There we go. So that's this one with the dots, that's the tangent line. The ones with the dash is actually the graph of the derivative. All right, well, we've got a sense at least of the thing we're shooting for. Fairly complicated, but let's see if we can get it. So again, hopefully you recognize this as another situation where we have, I'll use it f of g of x here, right? A function inside of another function. So if I want to find the derivative of this function, what I need to do is apply the chain rule, which will take the derivative of the outside function, leaving the inside function alone. Derivative of the tangent is 1 over the cosine squared, leaving the argument as e to the x inside. That piece is the first part of our chain rule. It's f prime of g of x. And then we multiply that times the derivative of the inside function, which is just e to the x. So that piece is just our g prime of x, right? So this is, of course, the chain rule that gets us our derivative, and it's just as easy as that. I mean, we're done, basically. I could clean it up a little bit and call it e to the x divided by the cosine squared of e to the x. And supposedly that's the function that we were looking at over here. Let's just see if it really is. So e raised to the x, all divided by the cosine squared of e raised to the x. I don't think I need that. There we go. And let's see if this works. Boom. So indeed the green function is overlaying the value of the slopes of the red function at every x. So it looks like we have a correct expression for the derivative. All right. All right, so to round us out here at the end, what I'd like to do is go back to the beginning. You know, we decided just based on a graphical investigation that there was pretty strong evidence that the derivative of the sine is the cosine. What does it take to formally justify this statement? I think this is a nice place to end. It's pure theory, and it's, I think, kind of a cool argument. Of course, you'd never be asked to reproduce this in a test setting, but I think for those of you who are heading towards a math degree or more advanced math, this would be good exposure for you. So let's go ahead and get after this. So off we go to the races for a formal justification. So let's see. So our hypothesis here, if I start out with the hypothesis, it's that the derivative of the sine of the angle, I'm going to call it the angle theta. Of course, this could be an angle x. I'm going to use theta. Is going to be the cosine of theta, right? I mean, if this isn't true, then everything we've done in this chapter just falls apart, right? So, you know, it all relied on this one derivative, right? In terms of the way we derived both the cosine and the tangent's derivatives. So it would be worth knowing whether or not it is really true. Okay, so let's go ahead and see if we can get a proof going. So let's see, if we wanted to find the derivative of the sine of theta, then of course all we do would be to take the limit of the difference quotient. So we take the limit as h goes to 0 of, on top it would be the sine of theta plus h minus sine of theta all over h, right? And here's where things get a little dicey because, I mean, what do you do here? I mean, you can't pull any h's out. You know, there's nothing to expand or change. It seems like we're just kind of stuck. I don't know about you, but it seems a little bit like, well, what do you do? And it actually turns out in this particular case, what you do is you make a picture. You draw a picture of what is, you know, what the sine of theta plus h means and what the sine of theta means, and see if you can make an argument about it using the picture. So this is a spot where sort of geometry in the unit circle comes in, and it's kind of a fun picture to draw. So I'm going to go ahead and draw it. We're just going to draw an arbitrary angle on the unit circle of theta. So I'm going to draw it just in the first quadrant, but we'll assume it's just sort of a piece of theta, or sorry, a piece of the unit circle. I want to draw it big enough so you can see it. Let's see, so that'll probably work. Okay, so this is, the unit circle. So if I draw an arbitrary angle theta on the unit circle, should have my drawing tools out here to begin with, sorry. I'll just leave this up here. So an arbitrary angle theta will start at this point. This is the point, I guess, 1, 0 on the unit circle. Let's say we go up to some spot like, I don't know, I'll draw it like right here. So that would be an arbitrary angle theta. Okay, so that means that if we dropped a perpendicular here, then this guy's x-coordinate would be cosine theta, and this guy's y-coordinate would be sine theta. So I could say something like this, if I extend this out a little bit, and sort of kind of think about this distance right here. So that distance right there, that's going to be sine theta. Okay, and I guess this distance right here, how do I want to draw it? I guess about, I guess I'll do it right here and here. That's going to be cosine theta, right? Yep. Okay, so that's what we mean by sine theta, but what would we mean by sine of theta plus a little bit more, an h? In fact, an h that's getting very, very small and going to 0. I'm going to draw it exaggerated, but, so let's say we add a little bit more to that angle, right? So if I add a little bit more to that angle, and I'll just sort of draw this as, so I add a little h to that angle, I get to this point on the unit circle, right? Which then gives me sort of two new locations. Let's see. So it'd be like here. This would be the sine of theta plus h, right? And here I'd get sort of drop a perpendicular down to here and call this distance the cosine of theta plus h. I need a little more space. All right, well, now at least I have a sense of what the sine of theta plus h is, but, what would be really nice is if I could somehow relate that to, say, the sine of theta, or rewrite maybe the difference between here. So that's kind of interesting, because you can see that the difference of the sine of theta plus h minus the sine of theta is a distance in my drawing. And I'll give you just a second to sort of soak that up. This thing is some distance in my drawing. Does anybody see what that is? So in other words, if I wanted to replace this using a drawing with a distance in the drawing, then it looks like it would be this distance right here. I'm going to make this a little bit bigger. I forgot to do that. See, because this is sine theta plus h, this is sine theta, so the difference between this and that is just this distance right here. In other words, it's sort of like if I extended this little line here horizontally, that distance is this little yellow, or pink distance right there, right? And so it might be worth us sort of blowing that piece up and asking sort of, well, what is going on there, right? And see if we could kind of figure out what that length is in terms of, I guess, some other unit or h, a cancel, something, I don't know. But the idea here is to sort of try to figure out how that relates. So what I'm going to do is I'm going to take this little triangle here and draw it over here, bigger. So I'm sort of exploding it. I'll try to draw it sort of somewhat in perspective. Now I know that this piece right here is an arc of a circle, but keep in mind that we're letting h go to 0, right? So in other words, this little extra angle, we're letting that get smaller and smaller and smaller. And of course, as those 2 points get closer and closer together, the arc on that circle gets more and more approximated by a line, or closer and closer to a line. So what we're going to do is we're going to say, well, that is just basically that, right? It's like a little right triangle. We know that this guy's angle right here, or sorry, this guy's length right here is the one that we're after. It's that thing. It's the sine of theta plus h. Yeah, this isn't going to fit very nicely, isn't it? I just didn't plan my drawing out as well as I'd have liked. So I'll just draw it up here. So that side right there is equal to the sine of theta plus h minus the sine of theta, right? That's what that distance is. We'll leave it in pink. And the big question is, well, how do we get something else after here? Okay, so one of the things that we decided is that earlier in the course we decided that that if we know the angle here, right, in radians, that's equal to the length along a circle times the radius. So so this length right here is equal to r theta. No, I shouldn't say theta. R times h, which is the angle associated with that side. But the radius, of course, of this circle, since it's the unit circle, is just 1. So so this is the same thing as 1 times h, or just h, right? So this distance right here is h. So in other words, that distance is equal to that value, right, of the angle creating that arc length, which we're approximating by a straight line, right? So now what we notice is that if we knew this angle, then we could call, pink over blue the cosine of that angle, right? So the big question is, what is that angle, right? And it turns out that that angle can be shown to be equal to theta plus h. So let's see if you can follow the argument here. So this whole angle is theta plus h, right? And this is a right angle here. So that angle right there is going to be 90 minus theta plus h. But of course, as this point gets close to that point, then that line becomes a tangent line to the circle. And so this angle plus that one is equal to 90 as well. And since this one is the complement to that one, that means that angle right there has to be the same as theta plus h. So this angle right here is equal to theta plus h. And so now we can see that this thing over that, blue over pink, is, pink over blue, is just the cosine of the angle here in orange. So this big argument gets us to this spot, right, where we can say that this is just the limit as h goes to 0 of the cosine, right, of theta plus h. And of course, if we think about what the cosine's doing as h goes to 0, um, um, this is just going to be equal to the cosine of theta. And that's the argument. I think it's kind of a neat one because you have to do so much digging and fine-tuning inside of the unit circle to kind of rigorously approach this. And of course, it really depends on one thing for sure, and that's this idea that the angle measurement be in radians, because when the angle measure is in radians, of course, then this arc length argument can be made. And this is really the heart of the reason why you learned about radians, is because in calculus, if you work in radians, then the derivative of the trigonometric functions are nice and easy to work with. If you're working in degrees, then they actually are not so nice to work with, and you have to deal with the chain rule to rewrite the argument in radians and chain out the degree, I guess, dilator inside of the argument. So Ryan, this has to do with why your approximation didn't work earlier in the semester for sine x over x. So nod to you here. You might think about that a little bit. We could talk about it now when I come back about why that wasn't working quite right when you were in degree mode with your calculator rather than radians. So yeah, that is sort of a good place to end. We've rigorously proved, right, that the derivative of the sine is indeed the cosine. So all the work that we've done in the section is indeed resting upon solid foundation. Okay, that's it for today. I'll be back tomorrow and look forward to talking to you then. Have a good day, everyone.